Good morning to our participants from Europe. Good afternoon, good evening to our today's participants from China. Welcome to our webinar. Our subject for today is about Mflow testing, mainly focusing on ISO 1133 and a little bit on ASTM. My name is Helmut Fahrenholz and I'm industry manager here in Zwickroll in Ulm. My background is a mechanical engineer. I'm here since 1987, so already quite a long time, and I'm industry manager since 2001, which also makes already 24 years. In that role, I work as a member in several national and international standard committees. I'm convener in ISO TC61. This is plastics. SC2 is testing methods, and the work group 1 is about static properties. I'm also a convener in DIN for a work group in the field of hard and soft foam materials, and I do the liaison between ISO TC61 and TC45, which is rubber, and I do that in a specific field of foam testing. Yeah, this is about my personal background. From here on, I will switch my camera off so that you can see the screen a little bit larger. I will do it now. And we start into our today's subject. We will talk about, let me do this. We will talk about a little bit the basics of Mflow testing, the different procedures. This can be quite complicated sometimes. I will present about one of our new products, the Mflow series, and let's say the way how you can use this. I will talk about programming of Mflow sequences, and shortly present the Aflow, which is a more automatic Mflow testing. So this is our program for the next, I would say, about 30 minutes. Yeah, let us go into it. I guess that some of you will be quite specialist and know about these things, but it's always good to repeat about the different methods that are standardized in ISO and also in ASTM standards. So when we talk about a Mflow tester, it always consists of a heated barrel, a die at the end here, a weight piece, a piston. So this is the minimum that you need to be able to do a Mflow test. And when we talk about this method A, you start to place this standard die, which is 2.95 millimeters in diameter and 8 millimeter height, into the barrel of the machine. You heat the instrument to the melt temperature of the polymer you're going to test. And then comes the first obstacle. You determine the polymer amount that you need for the test. And now you can imagine if you have a polymer which has a very high melt flow rate, so which is running very fast, you will need more polymer. While if you measure a polymer of a very low melt flow rate, you need a smaller amount. So here you have to make a first estimation about your material. So when you know this, it will be probably between 3 and 8 grams of material. You weight it and you fill it into the barrel and you compress it by hand pressure, so to compact it a little bit. Once you have the material in the barrel, you place the piston and you let the polymer heat up for 5 minutes. So this is the preheating time, which is described in ISO 1133. Now it can happen that you have too much material in the barrel. So you may be able to purge a little bit, means to push on the piston but you have to do it only up to 2 minutes before the test starts. This is because of, let's say, creep behavior of the polymer melt. So this is to avoid any influence on the later result. So during this preheat phase, normally the piston will slowly go down, and you have the first condition is you have to wait 5 minutes, and then you start the test when the piston is 50 millimeters above the die. So during the test, the piston will go down. You cut the filaments and you weight the filaments. So in the easiest or in the most simple method, the cutter turns in a constant time interval. So it means you know how much time was needed to produce a filament of a certain weight. So you have a weight and a time, and with the weight and the time, you can convert it to the MFR value, which is presented in gram per 10 minutes. So you do not measure 10 minutes, you measure to a different timing, but you convert all the results to 10 minutes. Yeah, this is the method A, and as you can see, this method A is a very manual method. So you sit in front of it, you have to watch what happens, you have to collect the filaments, you have to weight it, and so on and so on. The advantage of this method A is you can use it for all kind of materials, thermoplastic materials for sure. You can use it for filled grade. So if you have fillers in the material, for example, glass fiber, and the distribution is not that homogeneous, you can still measure it. You will see it in the result. So you will get a little bit fluctuation, but you still get the result in gram per 10 minutes. Another method is called the method B, and the method B is more automatic because in the method B we measure the piston travel, and by measuring the piston travel, we get the extruded volume. So we have a barrel of a certain diameter. We know the piston travel, and so we can easily convert to a volume. Furthermore, the method B, as we have a travel transducer and as the machine knows at any moment where the piston is, you have much more possibilities to control the test. So the procedure is very similar to that one of method A. So we have a preheat time and so on. We have 5 minutes of preheat time. We start the measurements at 50 millimeters, but then once we have started the measurement, we measure the piston distance. And now I can either work in a time-based concept, as we did for method A. So for example, cut every 5 seconds or 10 seconds or whatever. But I could also work in a travel-based sequence. So for example, to say I have a 30 millimeters of allowed travel in the barrel, and I do one measurement, for example, every 3 or 5 millimeters. At the end of the test, so the end of the test is 20 millimeters above the die, so we are not allowed to use the real end of the barrel. And once we have finished these tests, we have to clean. And cleaning is a very, very important point in method A and method B and whatever, because if you have any little remains of material on the wall of the barrel, on the piston, in the die, or wherever, it will probably influence your result. So cleaning is a very, very important point here. The advantage of method B is that you can use it for a very, very large range of MVR values because we do not need the cutting. We have a direct travel measurement, so the range of values we can measure here is very, very large. So for example, ASTM indicates that it can be used up to 1,500 gram per 10 minutes, and in some cases we also measured even more than this. Yeah, this is method B. The conversion between method A, gram per 10 minute, and method B, cubic centimeter per minute, is the melt density. So means is the density at the melt temperature. Yeah, there's another method which is quite interesting for people who are interested to see more about the viscosity curve or to measure on different points on the viscosity curve. This is the method D. This method D is also called the multi-stage test. So here you do the preheat time as we had it before in method A and B. But during the measurement, you change the weight. So for example, you start with 2.16 kilogram, then you do a measurement, for example, with 10 kilogram, and then maybe a third measurement with 21.6 kilogram. For being able to do this, you need a type of machine that is able to change the weights during the test. And this is the picture that you see here on the right side. We call it the Aflow. This is a machine which is able to do this method D. Yeah, let's do a little resume about these method I presented. So we have method A is the manual version. The result is gram per 10 minutes, and you can use it for both for unfilled and for filled thermoplastics. It is not very, very adapted for frequent testing because it needs a lot of operator intervention. So when you do this test, you can normally not do anything else. You have to concentrate on the test procedure. If in quality control, or you look for quality control and more regular tests, then typically you will apply the method B, either as I explained it before, in a timed measurement, or you can use the piston travel per unit of time. So you can also work in a travel-based sequence. And here the big advantage is in method B, the operator can start the machine and the machine can do everything until the end of the test. Means the operator just comes back for cleaning at the end of the test. The result you get out of this is the MVR in cubic centimeter per 10 minutes, and you can do the conversion. It is mainly used for non-filled thermoplastics because if you have fillers, you have an MVR, this is okay, but you don't have a constant conversion factor because the melt density will have a certain fluctuation with the homogeneity of the glass fiber distribution in the melt. Nevertheless, this is the typical method for frequent testing. But if we go on, we can combine method A and method B. Means we work in the method B mode using the travel transducer, but still use extrudate cutting. So this will allow us to determine the weight. And when we use this combined method A and B, we can determine the melt density, and we get out of the machine a directly measured MFR. Even so, we are in a test sequence which is similar to method B. So this is a very nice method, especially for frequent testing, as it is completely automatic. There is another method which is described as method C in ASTM, but which is also present in the ISO standard. This is the use of a half-size die. So this means we use a die of half diameter and half height. And such a die will shift our results approximately by a factor of 7 to 8. So the half-size die is used if, for example, you want to measure very high melt flow rates, or let's say a material that shows a very high melt flow rate using a standard die. If you use this half-size die, these results will go down by a certain factor. You don't have a direct comparability with a standard die, but you can intercompare with people also using this method C half-size die. So it's a way, for example, to work in method A, but to measure very fluent, very high flow materials. And last but not least, we have the method D, the multi-stage test I explained before. So this is roughly the 1, 2, 3, 4, 5 different methods that we find. And you see there is a lot of combination and possibilities. So that sometimes it's a little bit difficult to keep the overview in all of that. Yeah, if we, let's say we can show the whole test procedure in such a diagram. We have here on the y-axis the piston position. So we start with a completely filled barrel, and we have here the timing. So if we want to show what I just explained, you see here you have a certain time for preheating. This is 5 minutes. So in these 5 minutes, the piston will somehow move down. There is a certain area where purging is allowed. Then we have to wait another 2 minutes. So in ASTM, it's complete is 7 minutes of preheat time. In ISO, it is 5 minutes plus the time you need to approach to the starting point of 50 millimeters. And then you start the measurements. So it means when we apply ISO 1133 part 1, the time between end of 5 minutes and the approach time can be a quite big variable. So, and it depends on what is the flow of your material and how much material did you fill into the barrel. So if you have a low flow material and you fill up the barrel very, very high, then this time here, this approach time, can become very long. And for some polymer is no problem at all. But if you have time-dependent polymers, then this can become a problem. And therefore, we have a second part of this ISO 1133 standard, and this addresses moisture-sensitive and time-dependent material. So if you have a risk that that this approach time, let's say, or that the timing plays a bigger role for your results, or that your material is moisture sensitive, it is strongly recommended to apply the part 2 of ISO 1133. Typical materials is, for example, polyethylene terephthalate, PET. You can also use it for polyamides, for example. So all these materials that are not, let's say, showing a flat MVR diagram. Talking about ASTM, if you apply ASTM, it is in many aspects very similar to ISO 1133 part 2, because also ASTM has a quite narrow starting point in terms of position in the barrel and in terms of timing. So ASTM is always very, very narrow. Yeah, if you ask, so if you have a certain polymer and where do you find um, the temperature and the weight to be tested? This in ASTM is directly written. There are a lot of examples in the testing standards, so which is ASTM D1238. In ISO is a little bit more complicated because it is not any longer in ISO 1133, but these indications you find it in the specification standards of each of these polymers. So as you need to find this specification standard, there is a certain site on our internet website where you are able to find such a table, and you can find out according to which standard you have which testing conditions. Yeah, maybe a quite interesting question. We are talking about MFR and MVR, so melt flow rate and melt volume rate. And we can imagine this relates somehow to shear rates and to viscosity. So when we do or when we talk about dynamic viscosity, it is a measure of the fluid's resistance to flow. So we can imagine if you have a two platen and you have the fluid in between, so you apply at a certain speed of the upper platen, you apply a certain force, and this force varies with the viscosity of the material. We can apply the same for a tube. So we will have a flow in the tube, which is probably, if there's no slip, which is probably zero close to the wall and which has its maximum somewhere in the center of the tube. So by doing this approach, there is a certain calculation. We will be able to do a diagram of shear stress and shear rate. So the shear rate finally comes from the movement of our piston in a melt flow tester or in a capillary rheometer. And by the weight that we put here, we know something about the apparent shear stress that we apply to the material. So there is some conversion, so there's a lot of formula. What is interesting is that the shear rate, if we calculate it for our standard die, the shear rate is directly connected by a linear factor to the melt volume rate. And we can do the same for the shear stress. And the shear stress is directly connected to the mass we have on the machine. So far, so good, but all this is apparent shear stress and apparent shear rate. It is apparent because there are some, let's say, some odds. So in the intake of the die and at the out, there is a, let's say, a flow which is not that, how do you say, linear. And so there are some smaller mistakes that come into it. And normally when we do these measurements or we convert directly, we have no correction like the Barclay correction or the Rabinovich correction or what else. But anyway, if we would do our test at different shear stress, means like we see in the method D, we measure at different or under different loads, then we will see different shear rates, means different MVR values. And we could create an apparent shear stress, apparent shear rate diagram. And from that, we could also convert it back to an apparent viscosity over apparent shear rate diagram. And now we are very close to classical rheometry conditions. So that we could show such curves even using a melt flow machine. So what we did here is just some measurements with different sizes of die. It is different diameters. We just wanted to show here that even though the MVR value is completely different using different die diameters or die ratios, in a shear stress shear rate diagram, we are come very close by. As I told you, it is apparent shear stress and apparent shear rate. Therefore, we see small little differences. But anyway, this is the connection between viscosity and melt flow rates. Another thing that you can do when using such melt flow instruments is the kind of fast measurement of intrinsic viscosity, means the IV value. So this is something normally you do with an open load viscosimeter in a, let's say, in a polymer which has been solved in a solution. But it is known that there is a correlation between the IV value and the melt flow rate. So once you know the conversion between melt flow rate and IV, you can easily reconvert. And the advantage of such method is that it is quite fast. So what you need to do is, this applies mainly to polyethylene terephthalate. What you need to do is you need to really dry it very, very good. So you have to come down to a moisture level, let's say below 50 to 80 parts per million. So which is really very low. You typically do it in a vacuum condition, in a vacuum dryer, maybe with LN2 rinsing. So you really have to be very careful about the moisture. But if you manage the moisture, you can measure quite constant and reliable melt flow rates. So you have an idea about what is the level of degradation you had, for example, in a recycling process. Yeah, let's come a little bit to the different instruments. So our newest machine is the Mflow series. We released it last year. Mflow stands for a modular design. So it is always the same type of instruments. You can have it in different versions or specifications, starting from a more or less manual machine on the right side over a machine that has a weight lift that can, let's say, be more automatic, or a machine like this one here, where you have all the standardized test pieces or masses already in the machine, and you just pre-select by this little knob that you see here. You push it into the right holes here, and then the machine use this weight. If we go a little bit into it, so this machine is always equipped with a travel transducer, and so it can do method A using the cutter, method B using the travel transducer, combine method A and B by using both, but it is still a little bit manual, as you have to place the weight by hand and the piston and the weight by hand at the right moment. You can also use it for method C. You can use it for very high flow rates. You can use it for intrinsic viscosity conversions. So it can do everything you need, but it stays a little bit manual. If you have let's say go like this. For doing the test sequence filling, you have a little funnel. You have some means to be able to bring the material properly into the barrel. You have this travel transducer here, which is in place under the piston here, so it measures the travel of the piston. There's no mechanical conflict, so if you use a weight lift station, so have a more automatic machine, the piston travel transducer just stays in place. So here's a little bit little opening so that nothing goes wrong. And if for cleaning and filling, you can turn it around. You have a special position for the travel transducer to have more space to work. Yeah, on the other side, you have the cutter. Let's say from the experiences we made over the last years, we have modified the cutter a little bit so that it goes more out of axis in order to better avoid that material can glue or stick here to the cutting mechanism. There is a certain position for the cutter. If you want to clean here, you can just tell the cutter rotate by 180 degrees so that it is on the back side and you have more space to access this area. And if you have to replace, for example, the cutter blade, or you have to clean it better, you can easily take the whole head out and place it back again. So it's a easy dismounting. This is experience, for let's say practical experience at the end of the day. On the machine, you have a little holder so that you have all the tools in a place so that they are not somewhere around on the table. This is to make the life for the operator a little bit more simple. Here on the base platen, you have a little, how do you say, little board, a little something that avoids when you take out the die and it falls down. Sometimes it tends to roll away, and as the die is very hot, you have the reflex to grab it by hand, and this is not so good for your fingers. And therefore, we put a little something here in the base plate so that the die cannot roll away. Here on the right side, there is a numbered space for the filaments. So when you do the method A in the cut filaments, you can first place it here and then bring it to the scale for the measurements. Yeah, maybe here you see that the machine is always equipped with a controller and some software. So you have a lot of functions already in this inbuilt controllers. And one of the main point is we show the diagram I just showed before. So you have the piston position and you have the test time. And here on the red axis, you have the temperature. So during the test, you always know what your machine did, because you will have this graph. So in the preheat time, you can see if the material was pushed or if the piston was held for a certain time in order to manage this preheat time. You have the starting window. This is, for example, the window according to ASTM standard, and you see the measurements. So here, this is probably the 50 or 48 millimeter ASTM position for the start of the test, and then you do the cutting or the measurement in this area. So you know everything about the timing and the movements and so on. So you have a very good traceability of the test sequence. So when we are able to show this diagram here, sure, we are also able to show the speed. And the piston speed, as I showed before, directly can be converted into cubic centimeters per 10 minutes, so which corresponds to the MVR value. And then you get a diagram like this. So here, this is a polypropylene, so the material has no degradation, no uptaking, nothing. So then you get a straight line. But if you have a material that reacts at the melt temperature, then you will see here curves that go up or that go down and that do anything. You see small little peaks here at the points of measurement, and that tells me that we used the cutter. And it also shows that this diagram is very, very sensitive. So the small moment where the cutter passed by the hole of the die already gives you such a small indication here. So you really can see a lot of things by these diagrams. And this is always available in the inbuilt controller. Yeah, the weight lift allows you for a completely automatic sequence. So you put the weight you want to use here, and there is a pneumatic lifting mechanism that places the weight at the right moment. It can lift the weight if in the preheat time the material runs out too fast and you risk to lose the material, so it will automatically take it away. There's also an option to hold the weight in a certain position, and there's also an option here to clamp the piston so that you have a completely unloaded piston during preheat time. This is something you may use when measuring high MFR values. Yeah, and then we come to this slide here. This is finally the different options. So when you measure melt flow ratios, let's say below 30, then you normally just can put the piston weight in place, and you can just control everything with the piston weight. If you have very high flow materials or quite high flow materials, let's say below 200 grams per 10 minutes, then you need a little option to stop the piston. So means here in this first configuration, we take just the weight off, but the piston weight remains on the material. While here with this clamping option, we completely stop the piston. So this allows you to measure higher values. But if you have very high values, and I would say this is higher than 200, but you can sure apply it before, then you may use a die plug. A die plug is always a little bit a source of trouble, because it sucks a little bit the temperature from the die. So if you can avoid it, But if you have very high flow material like a melt blow polypropylene, for example, you cannot go around, and you need this die plug. So you have 3 different possibilities how to work over different ranges of melt flow rates. Yeah, cleaning is is the bad side. Because you have to clean the barrel, you have to clean the piston, you have to clean the die. The hardest is cleaning the barrel, and here we can use the piston movement, so the weight lift, to do an up and down movement in order to shot little little cotton clothes through the barrel for cleaning, so that makes it easier for the operator. So there is a cleaning function for that. Yeah, in a controller, I already talked about it. It is always inbuilt. It does all the test procedures. It can do conventional, we call it step-by-step programming, where you program every step. But it also can do something we call the APC function. And this is a function where you just tell the machine, I want to measure a material, for example, where I expect a melt flow rate of 8. And then it reacts like if, let's say, it reacts in an optimized way to measure a melt flow rate of 8. So if your guess was good, then the procedure will be optimized for this guess. This is called APC function, and it makes the life for the operator much easier, as he does not need to know all the different possibilities that you have throughout the different standards. You will have this live MVR graphic as I showed you before, and yeah, it does everything you need to do proper test procedures according to the standards. There are some indicators. So, for example, this play or this start button, if it is red, means that the machine is not fully heated, so the operator cannot start the machine too early. If it is green, it is ready to start. If the play button is green and the stop button is red, means we are in the test and the test is running. And by the way, here you see such graphic during the test. And last not least, if all buttons are red, then something is wrong, and you will probably see an error message here on the display that tells you what is the source of the problem the machine identified. You can connect these Mflow instruments to a PC. Then you connect it to testXpert, which is our software that we use for all instruments that we provide. So whether this is a drop weight tester or an HDT machine, or if it is a static tensile tester or whatever, we always use testXpert. So you have always the same operator interface. It makes it easier to, let's say, program or to work with different machine of our brand. And you just can connect it, and in that moment, the PC overtakes the whole control of the instruments, and you have some smaller supplementary functions. Yeah, you can connect up to 6 Mflow plastometers to one PC, because often there's not much space in the laboratories, and then you have 6 times the software running on the PC, so to control each of these Mflow instruments. Yeah. Last not least, let me just explain a little bit about the Aflow and the simplified testing. And I would like to show you something. So we already know this type of temperature, the temperature here, this type of diagram, the temperature here, and the blue is the piston length, so the distance of the pistons over the die. So when we fill it up, we are often, let's say, around 100 millimeters above the die. We start to heat up the material. At a certain moment, maybe we push a little bit more to purge the material a little bit in order to be after 7 minutes in the window that is, for example, described by the ASTM standard or by the ISO standard. So this is a typical test procedure. In a manual mode, you would have to tell the machine exactly what to do in order to reach this little window, the starting window, at the right moment. What we can do when we use the Aflow is we can work in speed control, or we can work in load control. And this allows us to identify very early what is the movement of the piston, so what is the melt flow rate to expect, and then the Aflow can identify, for example, do a check measurement after 3 minutes or so, then decide, okay, with the melt flow rate I see already at this moment, I have to give a higher preload at constant speed. So I just push it down to a certain position that I pre-calculated, and so to run the last 2 minutes under the test load and to come exactly into the starting window. Because if we would go not have this preloading moment here situation, then it would just go down here, and after 7 minutes not be in the right piston position for the start. So this is a way to organize the test sequence in a very automatic way. Yeah. So this is something the Aflow can do completely automatically. So you don't need to input anything. You just say, okay, I want to do a test, and then at a certain temperature under a certain weight according to a certain standard. And then you fill in enough material, for example, 5 gram, and then the Aflow looks by itself what to do. So this is a test procedure for a Mflow rate of 4.6. Here you see we run down a little bit faster. Here it pushes a little bit, then it comes to the right position and it does the test. If we have a higher Mflow rate, then it may look in a different way. So here we have maybe just the weight of the piston. We do a first measurement. We see, under my selected weight, it will run quite fast. So I stop it until I'm here, and then we'll release here at 360 seconds and go down and still meet the window. So means with the Aflow, everything you have to do is to select the right standard, ISO or ASTM, select temperature and load according to the specification standard, fill typically 5 gram of polymer into the plastometer and start the test. So everything else the machine knows by itself. And it can also be a big advantage if you have a lot of different grades. You don't need a big organization of stored test sequences, because at each test the Aflow just knows what to do, as it has a certain intelligence. So far so good. If you want, please you can address to us and ask your questions later like you want. And I say bye-bye for today. Thank you very much for being with us. You find us on zwickröll.com, zwickröll.tv. You can find us on LinkedIn, but I guess as you have found this webinar, you know already how to find us. Have a nice day, take care, and see you next. Bye.